Dr. Ramaswamy, thanks so much for making the time to speak with us. You're an expert on climate models, and of all the areas of climate change science, there's a great deal of empirical work that's being done, and the area where there seems to be the greatest uncertainty is inevitably looking into the future, the models. How good are the models these days?
The first climate models came online in the 60s and 70s. And since that time, the very first models were just the atmosphere. Then became atmosphere and ocean, then atmosphere and ocean got coupled to land, and so on. So if you look at the evolution over the last 40, 50 years, the understanding of the system has advanced vastly. It's increased by a tremendous amount. So the models of today are incredibly better than the models which were there even 10 years ago or 15 years ago. But that's not saying that we have accomplished the job, because there's still a lot of details that we still have to reckon with, which impact the accuracy of the results or the uncertainties in the results. So the uncertainties, what we have gathered in terms of knowledge is what are the factors governing the state of the system. And that knowledge keeps increasing. One, due to modeling itself. As computers get more and more fast, we can do much more advances through modeling. But the other ingredient in this is observations. The fact that we have a continuous series of observations now spreading back 40, 50, and some observations go back to 100 years, but that length of the record is increasing. So as the length of record increases, you're gaining more knowledge about the system. The other thing is technology, instrument technology, measurement technology is also advancing, which helps you to understand more of the Earth's system. Satellites, for example, cover the entire globe now. We didn't have any satellites measuring climate parameters more than 40 years ago. So all this has resulted in advancement of the processes. So if you were to chart how the timeline has gone by in terms of increased knowledge of the processes, that is definitely advanced, but we still have a long ways to go to address the major uncertainties. The other thing is the demand for information is increasing. Previously, people may have been interested in just rainfall and temperature. Now there's a whole host of other variables people are interested in, and that puts a challenge on how you model it, and therefore uncertainties become greater because you're dealing with parameters that were never measured before. People didn't even think of measuring salinity in the oceans 30 years ago. That became a point only in the last 20 years, and now satellites can measure salinity, but that's now a new parameter that models have to deal with. So I'm giving examples of how the state of knowledge has increased, but the state of demand has also increased. And so now your models are put to greater challenges, which means they have to address it, but it also means that you have a lot of incomplete things right now.
People who are looking at how to adapt our city, they need more granular information about impacts in their locale. How effectively can you now support that information requirement?
So if you look at the climate models, let's say around the beginning of the century, 2000, the horizontal grid, that is the spacing, was about 500 kilometers. Clearly, 500 kilometers, you would need 10 Hong Kongs to fill that. But beginning of 2010, which is just in 10 years, the model resolutions had gone from 500 kilometers to 100 kilometers. And since 2010, the advancements have been so rapid in terms of the numerics of modeling that you can actually now have models which are working and demonstrated to be successful in explaining some phenomena which are at a resolution of 50 kilometers. So you're getting down there. It's still not enough, but you have prototypes of models at 25 kilometers, and these are global models. And so that's going to happen. Now, another thing that helps in addressing the problem of the urban locations is that even though you may have a model which is 50 kilometer grid, which might be the length and breadth of Hong Kong, that's still not enough. You can do what is called downscaling, where you can go down through well-established techniques and downscale parameters from 50 kilometer grid to 10 kilometers or even as fine as 5 kilometers. So there are technical possibilities to get down to the urban scales. Now, the one thing you have to realize is that since you're going from one model to another type of model, your uncertainties increase. Doesn't mean that it diminishes the value of the information, but you just have to be aware that the uncertainty has increased. And very soon, you're actually going to have models which are going to be very, shall we say, sophisticated, where even with the available computing that that's there right now, which may not allow you to go down to 1 kilometer grid size all over the world. That may be impossible. But you can do a clever thing, which you've already actually demonstrated, where you can do 1 kilometer grid size on one side of the Earth, and the other side of the Earth, it'll be 100 kilometers. So for example...
So you can focus it, yeah.
That's right. So 2 examples I'll give is in the Midwest, in the United States, tornadoes have really wrecked a lot of lives and property. So one of the questions is, how can we simulate tornadoes? Tornadoes require a scale of 1 kilometer. Typically, they occur over a space of 5 kilometers. To do 1 kilometer, we've actually done a prototype model where you have a grid size of 1 kilometer over the Midwest of United States, but it's 100 kilometers over Indian Ocean, the other side of the Earth. Similarly, you can flip it around and do 1 kilometer over Hong Kong and 100 kilometers over the United States with the same model with existing computing facilities. And these are now being tested out in terms of climate mode, because you have to also test out what information they give. Is it of good quality? But you have the wherewithal to do that. And as we go into what's called the exascale computing system, which is going to come about in 5-6 years, you will have the opportunity to go down to things like 5 kilometers grid size. So the day's not far off when you can actually do this in the same mode that you're doing now with 50 kilometer models.
You're beavering away in your lab at Princeton, and people just won't let you alone. They want information. What kind of information are city administrations asking you for?
That is certainly true. There is a very urgent and rising demand for information with confidence levels. It's not that people want to know rise in sea level to, let's say, the decimal point of a meter, but they also know on the confidence levels. So we have found that the way to do this, in the olden days, we used to just say, okay, here's the data from the model, have a good day. That is not the way to do it. Now we are learning that we have to interact with the stakeholders, sit down with them. And so I'll take the example of New York City, where there's an increased concern because the subways, in many of the subway stations and the systems in New York City are below sea level right now. So they are very concerned that with the rise in sea level, no matter what rate it happens at, it's going to be accompanied by surges during hurricanes and just tidal movements. And so they're very afraid the subways are going to be flooded out. So you have to work with them to figure out what is the information they need. And sometimes they will tell you what other information do you have about your model. For example, the modeling of the rivers in the city. How well are you modeling them? Is there some assumptions you're making which may be contrary to their anecdotal data, the historical data? So then they make adjustments to your model results based on what they perceive as maybe limitations or deficiencies in the model.
The application of your science is actually helping make the science better, in fact.
Yes, it's helping to make the science better. It's helping to make the interactions involving the output from the science better. We are learning from experience.
Ramaswamy, thank you so much for your time.
You're very welcome. It was a pleasure to do this conversation with you.